now that we've looked at vector addition and vector subtraction, how we're going to use this, we're also going to be using some vector multiplication. There are two forms that usually comes in, and you may have seen them in your courses before. But it's the dot product and the cross product. Both of these are forms of vector multiplication, but they work a little bit differently. So first, notation-wise, our dot product is going to be the vector A dot the vector B. Enough, just makes a little dot between them. Our cross product is going to be the vector A cross the vector B. Super easy to tell them apart. Notationally, they sound just like they're drawn. But the major difference between these is that the dot product will give you a scalar as an answer, meaning not a vector. You should just be getting a number, a magnitude, scalar value when you're doing a dot product. But the cross product will give you a vector as an answer. The other major way that these are different is the way that they're represented. So we write their general equation as your dot product is going to give you the magnitude of A times the magnitude of B times cosine theta, the angle between the vectors. Whereas your cross product is going to be the magnitude of A times the magnitude of B times sine theta. But then this is still a vector, right? So it's going to be multiplied by the unit vector of it. So these are our major differences between dot product and cross product. Cross product, our general equation. I'll give you the general equation for each of these. Cross product we're not going to see for another few weeks, but I wanted to introduce it now so that you see the difference. Our other general equation for the cross product here is going to be in component form. This is in Cartesian form for the vector. It's going to be AY times BZ minus AZ times BY I hat minus, that's important, that minus is very important. Again, we're going to go through the derivation of all of this a little bit later, but I wanted to show you the difference. It's going to be minus AX times BZ minus AX times, AZ times BX J hat plus AX times BY minus AYX A hat. So this is the general form of the cross product. Both of these are equal. All right, so your general form may be in this top version or maybe in this bottom version. For our dot product, which is the one we're going to be getting into today, our general form is going to be this equation, or we can use the dot product is AX times BX plus AY times BY plus AZ times B. This is our general form of the dot product. So the reason this is because of some of the properties of the dot product. Anytime there is an angle between the two vectors that equals 0, means we have just two lines on top of each other, right? So if this is A and then this is B, it means that their dot product is going to be 1. Because they lie entirely on top of each other. So A dot B in this case is going to be 1. However, if they're perpendicular, so if A goes straight up and vector B goes straight out, then the dot product of A dot B going to be 0. So that's why you don't see any mixed AY, BX terms or anything like that, because those values would be perpendicular to each other, so they automatically 0 out. Now, some of the properties of the dot product work a lot like regular multiplication. So I've got this little cheat sheet here of products of the dot properties of the dot product. So it works a lot like regular multiplication. You'll see that A dot B is the same as B dot A, which is the same reciprocity we do regular multiplication with just values. And we'll see that the commutative properties work in the ways that we expect. So these are some general rules we can expect to see with our dot product. So that may be all well and good, but what does the dot product really mean, and why do we care about it in statics? So we have 2 use cases in statics for this, which is, 1, if we want to find the angle between 2 vectors. This is going to be a really big one, especially now that we're working in 3 dimensions. You may not always have all of your angles given to you. You may not know the angles. You may not be able to figure them out trigonometrically. So here we can figure them out using the dot product. And we'll go through an example of. And then 2 is because it provides the projection of one vector onto another. So what that means is if I have my vector A here and my vector B here, what the projection means is it is what goes perpendicular out from one onto the other. So the projection of A onto B strikes B perpendicularly. So it would be this comes down from A, the projection. If I were shining a light down on it, how would vector A look on top of vector B? Right, so here's the shadow on top here. This portion would be the proportion of A onto B. And remember, it's a scalar value. It's not actually giving you a vector. It's giving you this distance length here. This is the value that it gives you, the dot product, when you do A dot B. It's giving you this distance length. The projection of A, what proportion of A is hitting B. And this works still if this is rotated. So let's say it looks something like this. It would still be perpendicular, this line that you're projecting on. Right, so this is perpendicular to the vector. It would be this distance here that is being projected onto it. And we can already kind of see how this would be really useful for finding our x and y components. So let's work through a couple of examples. So in this example, it's asking us to find the angle between the vectors, where it gives us vector A and vector B already in Cartesian form, not even drawn out for us or anything. We don't need to figure any. Given in Cartesian form, what is the angle between A and B? So since it's not even drawn out, we can't even assume what an angle would be just by looking. What we'll have to do instead is do the dot product. Now, if you'll recall, our dot product definition that we just went over is going to be AX BX plus AY Y plus AZ BZ. So now that since it's already in Cartesian form, it makes it really easy to write out what these are, right? So our AX BX, we're just multiplying these 2 terms together. 18 times 2. Multiplying our Y terms together. Notice we've only been given J hat here with no number in front of it. That means it is just one single J hat. If there's no number written in front of it, it's implied that it's a 1. So that will be 1 times 3 plus, is that a negative 1? I covered it up. No, it was positive. It was a plus. Plus our z components here, 30 times 6. So we're going to get the dot product of a dot b equals 219. Plug that into our calculator. Okay, so that's great and all, but how do we get our angle from that? Use our other definition of the dot product to backtrack into. So our dot product, a dot b, had the additional definition of being the magnitude of a times the magnitude of b times cosine theta, which does mean we'll need to come back and find the magnitude. Again, should be fairly straightforward at this point. It's essentially just our Pythagorean. Let's move. Okay, we know a dot b is 219. Delete this guy. Move him. Let's move him down here. A dot b is 219. All right, we can find our magnitudes. It's just our square root magnitude of a, square root of 18 squared plus 1 squared plus 30 squared, which will give us, type that into our calculator, 35. And for b, of course, it's the same process, 2 squared plus 3 squared plus 6 squared. Plug that into our calculator, we're going to get 7. So now I know the magnitude of a, the magnitude of b, and what my dot product is. So I can rewrite this equation down here to solve for theta. So if I do that, our theta inverse cosine of our dot product, a dot b, over the magnitudes a and b. In this case, we're going to have inverse cosine of 219 over 7 times 35. So when we plug that into our calculator, we get an angle of 26.6. So that's our first use case, finding the angle between two vectors. So now we'll look at an example projection. So this says at the top, determine the magnitude of the projection of the force onto the pole. Pole is our blue guy at the bottom, and the force is in yellow color. So they've provided us with the force, and then they provide us with these measurements here. If it's a little unclear, this is 2 meters, this is 2 meters, and then this is down 1. So lucky for us, they already gave us the force in Cartesian. Don't need to do anything. Do, however, need to get a vector for this pole. Again, since we don't have a vector for it, we'll need to make one position vector, as we did in the last section. So our position vector, r, is going to be this distance along the pole. This is going to be our r vector from the origin out to the connection to the ground. So our r vector in this case, we can see it's coming out by a positive 2 meters in the x direction, or in the y direction, as well as in the x direction. This is the x direction here, the positive 2 meters, the positive y direction, this 2 meters, and then we're going down by 1 meter in the negative c. And that's, of course, coming from the origin. So our vector is going to be 2, 2, negative 1, out from the origin to the point. So now that we have the position vector, we can find the unit vector from this. So our unit vector of r, the vector itself, over square root of 2 squared plus negative 1 squared. So we end up with a unit vector of 2/3, 2/3, and negative 1/3. Now to find the projection, our projection is going to be the dot product of f dotted with the unit vector. And that's going to give us the magnitude of our projection of F force along the pole. So I have my unit vector there. I'm going to go ahead and keep that. If I do my dot product, light blue, my dot product, again, is just ax times bx plus ay times by plus az times. So we're going to have ax times bx. That's going to be f dotted with u is 2 times 2/3. Then our y components multiplied together, 4 times 2/3. Then finally our z component, 10 times negative 1/3. 10 times negative 1/3. I plug that summation all into the calculator. I'm going to get f dot u dot product gives me the projection of the force onto the pole. It gives me a magnitude of 2/3 kilonewtons, which I'm going to write as 0.67 kilonewtons, since our original force was given in kilonewtons. This is the projection of the force onto the pole, the component of the force that's actually acting on the pole. Now, if I wanted to know this in component form, if I wanted this in the x, y, z Cartesian form with the I, j, k unit vectors, what I can do is I can take this dot product and multiply it by the unit vector. What this is going to do is turn it back into a vector with the force component still attached. So if I multiply it by u, then I get 0.67 times 2/3, 2/3 times 2/3. So I will end up with component, the projection components, going to end up with 4/9 I hat. Then now I'm going to do this number times the y component. It's going to be 4/9 j hat. And then the z component times my scalar value here, going to be 2/3 times 1/3 is 2/9 minus 2/9 j hat. So this is it in component form. If you ever want to go from component form or from projection form to component form, all you do is multiply by the unit vector. So let's write down those shortcut equations really quick. So those shortcut equations that you can use that are going to be really helpful are that angle between them is the inverse cosine of the dot product A dot B over magnitude of A times the magnitude of B. This is one really handy shortcut. Another one, if you want the scalar value, then your vector A dotted with your vector u, the magnitude of A, cosine theta. Now remember, we said our dot product was the magnitude of A times the magnitude of B times cosine. But in this case, if we dot it with a unit vector, then the magnitude is already 1. I already know that. So in this case, it'll be the magnitude of A times cosine theta. And this gives you, this is the value of the projection of A along vector u. This is the scalar form. If we want, we can get it in vector form, just as we did in this last example, which we also call the component form, the components along the line. And all we do is we take that dot product, A dot U, and we multiply it back by the unit vector. All we're doing is multiplying it back out by the unit vector. This will give us it in component. So this is a really great cheat sheet for using the dot product to find the angles and find the components along. I'd like to do one more example here. If you want, you can pause the video and try to attempt the example for yourself. If not, we'll just work through it together. It's up to you how comfortable you are with this material. Okay, so this is our final example. And you can see it's a little more complicated because I didn't even attempt to draw it out. I just stuck a picture in here. Now, it didn't come with all of the dimensions written in, so that way you change the dimensions and make the problems different. But the A value in is going to be 2 meters, and the B value that you see in the is going to be 4.5 meters, which I have written in there. So what they're asking for with this image is to find the angle theta between angles F2 and F1, as well as finding the projection of F1 onto cable AC. We see also this F2 is good. So the first thing we want to do is that since it tells us that we're going to find an angle, we know how we're going to do that, right? Just established that we can use this theta cosine inverse cosine, arc cosine, of the dot product of A dot B over the magnitude of each of those. Now, we do have the magnitudes. It tells us that F1 is 70 and F2 is 40. So in this case, our A and our B, we want to write it specifically for this case. It would be the dot product of F1 dot F2 over the magnitude of F1 times, which we already have is 70 times 40. But how do we find the dot product? Well, we know our other definition of the dot product. A dot B is AX dx plus AY y. AZ. So using this, we should be able to determine what our dot product is that goes in the top part of this term so that we can find the angle. Now the tricky part is going to be finding that AX, BX, all of those component pieces from F1, F2. So we're going to go about doing that how we did it in the last section, using position vectors to find the force vectors. Let's go ahead and look at F. Let's look at F1 to start. Okay, so for F1, we have these position vectors. Let's actually write, before we get into F1, let's write out all of our points, just to make sure we're on the same page with those. So our point A is located at an X value of 2. It's coming 2 out of the page with us. A Y value of -2, right? It's 2, but in the negative Y direction. Then a positive value of 3. Our B location going to be, we're located just on the y-axis. So it's over by 2 on the y-axis, and it doesn't move at all in the x or z. That's going to be 0, 2, 0. And the position of our C point, it looks like it is going back by -2 in the x direction, a +2 in the y direction, and then in the z direction, a +4.5. So now we'll find the position vectors. We have 2 position vectors. We have one going from A to C, and the other position vector along F1 is going from A to B. So these are the 2 position vectors. Again, the way we find those is vector subtraction. So it'll be subtracting for RAC. It is this subtraction of our C minus our A. So RAC, if we do -2 minus 2, get -4. The vector, I'm going to put it in brackets. -4. Our y component is 2 minus a -2 gives a +4. And then 4.5 minus 3, 1.5. So this is RAC. RAB is going to be exactly the same process. So this is B minus A. So 0 minus 2. RAB is going to be -2. Right here. -2. 2 minus -2. Going to be 4. 0 minus 3. -3. So these are our 2 position vectors. You can do these processes side by side, or you can do one after another. I'm kind of doing them simultaneously, just to kind of show you where my thought process is at, but you could do it entirely, working all the way through for RAC, or let's see, vector AC goes F2. You could go through all the way for F2 and find the vector for F first, or you can do them. So let's think about what our next step is. Now that we have the position vector, what's our next step? We're going to find the unit vector. Finding the unit vector from the position vector. Like, go ahead and get rid. I'm going to get rid of my text at the top too. Get rid of all of this. Keep just those vectors. So we can look at RAC, we can do the unit vector, AC, is RAC, 4, 4, 1.5, over the magnitude of RAC. Again, we do by doing the square root of our squares. 4 squared plus 4 squared, 1.5 squared. We plug that bottom part into a calculator and we divide each component by it. So we get negative, again this is a vector, negative 0.68, positive 0.68, and a 0.26. And that's a vector. And then the exact same process we're going to do for the vector RAB, we're going to make the unit vector UAB. That takes our position, -2 or -3 vector over the magnitude. plus is going to give us oh, I don't have it written down. I'll have to actually put it in the calculator. All right, so that gives us, let's see, square root of 4, square root of 4 plus 14 plus 9. That gives a value of 5.38. Negative 2, 5, 8. We have vector value negative 0.37. And 4, if I plug that in, that's going to be positive 0.76. And then a negative 0.56. 0.56. So that is our unit vectors, each of our unit vectors. With our UAC in yellow corresponding to F2, and our UAB corresponding to F1. So what we'll do is we'll multiply the unit vector times the magnitude. We're multiplying these guys together, unit vector times the magnitude of the force, multiplying UAB times F1, UAC times F2. And that will give us each of our two force vectors. I'm just going to write this in here. If I multiply, and multiply out, so F2 is 40, so I just multiply 40 into each terms. Put this in. Hold F2, negative 27.3, positive 27.3, 10.25. That is our vector F2. We do the same for F1. Multiply the magnitude of F1, which labeled on our thing is 70 newtons. Multiply it out into each term in our unit vector. Multiply each of these. And we get about negative 26, positive 52, and a negative 39. So this is our F1. This is our F2. These are our two vectors. Now we need to go back to the very beginning of the problem. Move all of this out of our way. Because the whole reason we did this was to find the components so that we could plug them into the dot product. Right? As you'll recall at the beginning, add the angle theta, the inverse cosine of the dot product, and that's what we were looking for. The AX, BX, AY, BY, AZ, BZ, all over magnitude of A times the magnitude of B. Now that we've found each of those components for F1 and F2, which we had, I'll write them again here. 1, and 2. I'm going to round these just to 2 significant figures for the purposes of this discussion. Simplify things a little bit, but you would normally probably include 1 or 2 decimal points here. So all you'll do now is just plug all of this in. We have everything now. We need to find the angle theta. That was our first objective, right? Find the angle between the two vectors. So we'll have inverse cosine, and then we can just start plugging everything in. Negative 26 times 27 plus 52 times 27, right? And that's just multiplying these across their rows, right? X components times Y, X components and Y components and Z components. Is that a negative 39 minus 39 times 10? Then the magnitudes were given to us, right? 40 and 70. Plug all of that into the calculator and finally have our angle. Our angle theta, the angle between them, 51.8 degrees. Somewhere around 52 degrees. I may have had some rounding errors in here, but it should be somewhere around 52. So that's the answer to part 1 of our example. But our example did have 2 parts. It asked us for angle between the vectors and for the projection of F onto cable AC, F1 onto cable AC. So to do that, all we need is that projection formula, which was the projection of F1 onto AC. Going to be the magnitude of F1 times cosine theta. That's it. The only formula we need. And we know we just found theta, and we know the magnitude of F1. We can look at 70 newtons there. 70 times cosine of 51.8. So the projection F1 onto AC going to be 43.2 newtons. That's it. So this is an example of how we'll kind of be dot product in combination with everything we've been working on up to this point, with our unit vectors, our Cartesian vectors, our position vectors all coming together to find the value of these forces.